All right, so today we're going to talk about the compound inequalities. So uh, I want to be kind of clear here in this video in case somebody should be watching this outside of my class. This particular video for everyone is about compound inequalities and versus or, and it's literally focusing on just the most common types. So the most common types of compound inequalities you have are the disjunction, and the disjunction is a type of or. Okay, compound inequality, and the conjunction is a type of and. And what I have shown on the graph here is essentially just kind of like what their picture looks like. Are there other graphs for or? Yes, there are other graphs for or. But for right now, we're just focusing on the most common type, which is the disjunction here in Algebra 1. Excuse me. And then we're also going to focus on the conjunction here in Algebra 1 as well. So that's what this video is kind of majorly going after. We're not going after any other types of and or ors, just to make that clear about this video. So let's go ahead and kind of get going at it here. So the very first thing we're going to discuss here is just what a compound inequality is in general. And a compound inequality in general is just literally going to be two inequalities or more joined together with the words and or. So essentially, right, it's like a compound solution you may have heard in science. It's just, which is a mixture of two or more elements. So a compound inequality is just going to follow suit with that. It's just going to be two or more inequalities that are joined together by the words and or. And let's talk about what happens if you have the word and or. The easiest way to put this is and your two inequalities must work together. And if it's an or, they can work apart from one another. Okay, I have another video about compound inequalities, and if you want a better explanation, I go through that one and I talk about it. You might want to just take a look at that, but for right now, to keep this video kind of short as possible, I just want to get into exactly what a graph may look like for the and or. But just do note, for the type for or, they can be disjunction, which means they can be disconnected from one another, meaning their graphs, while you're going to place them all on the same graph, do not have to have any sort of answers that go together type things here. So that's the idea here. So let's take a look at some examples, and then we're just going to get into solving some of them. So the example, all right, so we have this example. It says x is less than or equal to -2, or x is greater than 3. Now, the word or matters here because the word and implies that you have a number that is both less than -2 and greater than 3. Now, that would be literally impossible to have a number that's less than a negative but greater than a positive. That just isn't able to do that. There's nothing that exists that can do that. So this word or really matters here, because what I'm basically giving you is this idea of options. So there's two ways of graphing this. You can graph it with inequality notation, or you can graph it with this interval notation. I'm just going to stick with inequality notation because of state exams for us. So the example is x is less than or equal to -2. So what I would do is I'd go to -2. I would go to that boundary point and I'd put a closed circle. And then this inequality literally states that I want it to be less than, so I will shade to the left. And I will put that answer on the number line. So that one is done. And then I also go on the same exact number line. I will plot an open circle, another boundary point at 3. And it says to be greater than, so I will shade this to the right. Okay, and what you will find is that I've got a disconnected shaded and number line. So meaning that the shading from the first inequality does not connect with the shading from the other inequality. So that's why it's called the disjunction. All right, so they're disconnected from one another, but that's the importance of the word or. Okay, so the word or is you can have one or the other, and that's okay. So just putting that into practice, and we have some some basically just some problems, and essentially I'm just going to go over two of them. I'm not going to do the first one right off the get-go here. I'm going to skip down and I'm going to do number 3 here, and I'm going to do number 5. So if you're following along and you're going through this stuff, those are the ones I'm doing. So here we go. So 2x plus 9 is greater than 17. Or 5x plus 10 is less than 10. So these are my examples. So let's go ahead and get to it. So the first one, we're going to solve these. Now, these are two separate inequalities. So I'm going to solve them separate from one another, right? I'm not going to try to do these things together. I'm going to solve them separate from one another and then put their answers all on the same number line separate from one another. So with that being said, what I'll do is I'll write to solve this. So we'll subtract 9. So we'll start using the inequality or the inverse operations. So I get 2x is greater than 8. Divide by 2, divide by 2, and I get x is greater than 4. Then from there, I'm going to write the word or. So I'm going to go ahead and minus 10, and I get 5x is less than 0. Divide by 5, divide by 5, and I will get x is less than 0. So my compound inequality states that I want to have a number that's greater than 4 or less than 0, right? So again, if the word and was being used here, that'd be kind of tough because any number less than 0 is a negative. So a negative can't be greater, okay, than 4. And remember what I'm talking about here is that this value of x and this value of x are the same exact number. That's the important piece here, okay? So if you use, what is called, the reflexive property stating that a number is always equal to itself, okay, the word or matters because the word or essentially, allows you to use x one at a time. So the word or allows you to keep this x, when you plug it in, you're going to plug into just this one or just this one, because that's very, very important because the reflexive property states that a number is always itself. And because this x and this x are the same, we need to have separation of not plugging it in at the same exact time. Because if you plug in at the same exact time, then you break this property. Because there's no way that you can pick a number that's greater than 4 and is also a negative at the same time. So that is kind of the importance of this word or right now, because the reflexive property states a number is always itself. So when we have x in our problems, that x is the same x. The word or allows us to separate them. So because the word or, I'm now able to graph, at 4, I can put an open circle and shade to the right. And then at 0, I can put a boundary point and I can shade to the left here. Does that mean every or is always going to look like this? The answer is no. These are just the common ones, the ones that our state tests on for the Keystone exam. So these are the ones we go over in our course. Now, let's talk about interval notation here for a minute. It's not necessary to know. It's just a little extra right now. On your test, you're allowed to ignore the interval notation. But if you have an or, it's called the union inequality. You're going to use a union symbol. So basically what that says is that you're allowed to have two separate bins of numbers to choose from. So inevitably what you're allowed to do is you're allowed to go from negative infinity. So if we're looking on our number line, right, the farthest point to the left, okay, is negative infinity. And then that first section has the largest value of 0. Okay. Well, remember in interval notation, yesterday that I talked about was that it was the lowest value to the highest value. Well, the union symbol is going to demonstrate that I have multiple sections in on the same graph. So what you're able to do as a union symbol means, hey, you had a little bit of a break, pick back up at this number, and here is the smallest number that you will pick back up at. So in our example, we pick back up at 4, and then in that section, okay, the largest number in that section then is positive infinity. So with that being explained over here and to the left, if you see it on my screen here, explaining this, what I was just talking about, the interval notation is, okay, in this particular area here, right, what is the lowest number in this set? And then union is, okay, I've got a break in my graph, in my number line here, and then I pick back up over here. So again, the first set has the lowest number of negative infinity. It goes up to 0, and I use a parenthesis to end there. Okay, if this were a closed circle, I would use a bracket around 0. But then we use the union symbol. The union symbol is literally just like a big old capital U here. And then there's my break. So that union right here, okay, the union is basically saying, hey, you went over here and then you're picking back up at 4. Now it's a open circle at 4, so the smallest number in the next section is 4, and then it goes all the way out to positive infinity. So this is what that would look like. Okay, so next example is number 5, and then we're going to get into some and. All right, so number 5, we have some problems here, and it's got us that we're going to solve through. So here we go. So it says negative 3 times 2x plus 1. So I'm going to go ahead and distribute this, and I get negative 6x minus 3 is less than negative 15, or 1 minus x is greater than or equal to 5. So I'm going to go ahead and solve the first one here. Oh, sorry, I didn't really need to write the second one here yet. So the first one I just did a distributive property, so I'm going to continue to solve. So inverse operations, I'm going to add 3, and I get negative 6x is less than negative 12. And then I'm going to divide both sides. And now here's the important part. I'm dividing by a negative 6, dividing by a negative 6. So because this is important, I'm going to, highlight this. You need to remember that if you use an inverse operation and the value is negative that you are using through multiplication or division, you must flip the inequality. So why is that important? Well, this problem goes from having a less than symbol to now that it says x is strictly greater than positive 2. All right, so that's important. So remember, when you have that division by negative, you got to flip that inequality. On to the second inequality, so I'm going to subtract 1. Just be very careful. This is a negative x. So this is going to be negative x is greater than or equal to positive 4. Divide by negative 1. Divide by negative 1. Again, remember the same process things that I just talked about. Dividing by a negative, you got to flip that inequality. So it's going to be less than or equal to now negative 4. Throw the words or in between it really quick for your answer. And now let's just talk about going ahead and graphing this. So I need a number that is greater than 2 or less than negative 4. Now remember, by logic, this is important that we have this word or here, because the word or, okay, allows for disjunction between the two inequalities. All right, it means that you're allowed to have two separate sets of numbers, even though we know that x is the same value, but the word or allows us to choose one inequality to replace the value of x for at a time. meaning you don't have to replace both of those x's at the same time. Okay? The word or allows you to do it for one of them at a time. That's important here. All right, so here we go. So what I can do now is I can go ahead and graph this. So I'll graph the first one. So x is greater than 2. So open circle at 2, and then we shade to the right. And then we have a closed circle at -4, and it says less than, so I'm going to shade to the left. So basically you can see here the disconnection. Now let's just do the interval notation. And again, this is not something you have to know for Keystone exam. It's just something that I'm going over because it's something you're going to see later in another course, and just introducing it to you. So here we go. So the first set, what is the lowest number in the first set? So the lowest number, again, is -infinity, and any positive or negative infinity gets a parenthesis. And then comma, what is the highest value in that particular first set? It's a 4. Now, because it's an equal to, we bracket it. Now, because there's a gap in my information, meaning there's a empty space in my set, okay, meaning that to jump from one set to the next set, we use a union symbol. So union symbol. And then we start at 2, but because it's an open circle, it's a parenthesis. So 2, comma. And then that set goes all the way out to positive infinity forever and ever. All right, so here are the couple of things we're getting out of this thing. So notice we have disjunction, meaning one piece of this graph is pointing to the left, the other piece of this graph is pointing to the right. And that's okay because of the word or. Okay, now not all ors look this way. There are some other ors, but for right now, we're just going to be hyper-focused on the one that is the most common type of or, which is the disjunction. And then also we talked about this interval notation, and the interval notation, because of the disjunction, we connect them with a union symbol. And now let's get into seeing the most common type of and compound inequality. So on to the next. All right, so the next type that we have here is this and compound inequality. And basically they have a tendency to graph together. Well, there's a reason for that, is because when one is disjunction, the other one is working with in conjunction. So conjunction basically means that now, okay, what we have is we have this reflexive property where A equals A, which states that a number must always be equal to itself. Well, the word and, okay, now requires you to replace, okay, a number in. So for our first example here, okay, this now requires you to place a number in both this value of x and this value of x. That's the big important between and versus or. Or says you can do one at a time, check if it works, and if it does, good. All right, then it works. But the word and means you have to plug it in here, then over here, and as long as both of these are true, then it now counts as an answer, okay? So or allowed for true, false to be a solution. And the only thing that actually doesn't work for the or is a false, false. But for the or, you could have a true, false. But now with and, you have to have true, true, which means both of these have to be true in order for you to be able to graph your answer. And what happens is that this becomes the conjunction. And just to show that, I'll show you what a conjunction kind of looks like. All right, it's the conjunction. So the reflexive property, right, we have this, so we're going to still hold this in place, and now the word and just means you got to plug in a value for x that works for both inequalities. Well, let's take a look at what happens, right? So you need a number that is greater than -6 and less than 1. Well, let's just say we want to pick the number 3, right? So if I pick the number 3, okay, and we check it, is 3 greater than or equal to -6? And the answer is true, right? That is true. But if the word and is important because now that same 3 that you picked here, you have to also replace over here. So if you replace this with a 3 and say is 3 less than or equal to 1, the answer is false, right? Now, if this were an or, it's kind of like, okay, that's cool. And the reason for it is because or only needed you to plug it into 1 to get it true, and that wasn't an answer, right? But because the word and, it means you're going to have to start plugging in numbers into both of these, okay? Just to go through that again. So, okay, well, 3 made this one false, right? 3 made this one okay, but it made this one false. Okay, well, let's just choose another number. Let's start from x. Let's think of it on the side of x being less than or equal to 1. Let's pick a number like -2, right? Well, is -2 less than or equal to 1? And the answer is yes. Well, don't forget the word and means that this same -2 that I used here, I have to use over here. So I get is -2 greater than or equal to -6? And the answer is, well, that's true and true as well. So now let's talk about where does the number -2 on a graph, okay, appear on a number line in relation to the numbers -6 and 1. So at -6, we have a closed circle because it's less than or equal to. And at +1, we have a closed circle because it's less than or equal to, greater than or equal to, less than or equal to. So now we picked a number 2. Well, the number 2, if you notice, lies in between the two of them. So if you were to graph these inequalities separately, right, the inequality of -6 claiming x is greater than -6 would fly way past this this 1, right? And if you graphed the x is less than or equal to 1, you would see that these would fly way past the -6. But what does the conjunction show, right? Well, the conjunction shows, well, where do these two graphs overlap? And if you notice, -2 produced a positive answer while 3 produced a false answer. And what you can begin to gather is this idea of conjunction, is this idea of where do answers for both inequalities exist. And now looking at the number line, you can see that by seeing that this line overlaps with this line only in the middle. And this is the idea of what it means for them to be together, okay? So that's the idea of having them graph together. So meaning that this point connects, the idea of conjunction is the idea of connecting one point directly over to the next point, okay? And now as it pertains to the interval notation, just to talk about this for a minute, the interval notation, remember, is in a set of shaded area on a graph. You're going to tell me what is the lowest possible value to the highest possible value. So the lowest possible value in this set is at -6, and the highest possible value in this shaded area is going to be at 1. And now notice I'm using brackets because both -6 has a closed circle and 1 has a closed circle, so they get brackets. Now, the next thing I want to show for and, okay, because of the interval notation, okay, if you see that the lowest to the highest are just two numbers, like notice before, none of these are now infinity, that a common way of writing this without the interval notation and the way that you're going to be majorly tested on, okay, and the one that you really need to know as it pertains to your state exams is that same exact thing that if I took that interval notation and kept it into compound inequality notation would be kind of the same exact thing. What is the smallest value in that set of numbers? Well, -6 has to be less than a value of whatever x you chose, and it also then had to be less than or equal to 1. Okay, so another way of saying that is that this number had to be greater than 6, but less than 1. But if you look on a number line, you would say the opposite way. You would say that this is smaller than any number here, And any number here is smaller than this number. So that's why we just use the same inequality as of less than or equal to, less than or equal to. And now the equal to piece is basically decided upon still whether this is a open circle or a closed circle. So this is the conjunction, okay, inequality notation. Okay, this is the conjunction compound inequality notation, meaning they're together. So you have a set, which you have a boundary point all the way to the left. That is the lowest boundary point, which is the lowest value. And then you're going to have some numbers in the middle, that those numbers in the middle are going to be less than the numbers that are on the right-hand side or the far right boundary point, okay? So if you read a number line, you literally can pick any 3 points and go, hey, as long as you're doing them from left to right, you can literally say this point is smaller than this point, which is smaller than this point. So that's the idea. All right, and it's always going to be this less than or equal to. It's not like you're going to use a greater than here, okay? Because you read graphs from left to right. So this value is less than this value, which is less than this value. Now, when solving problems, you may get some tricky ones, or your teacher might try to set them up as this one is greater, okay, than this one, which is greater than this one. But when or when you solve them, but what you'll see, okay, is inevitably that you can use the symmetric property, and the symmetric property will always turn it into this one is less than this one, which is less than this, which is less than this, okay? All right, so with that being stated, and because this is the most common type of and compound inequality, is the conjunction, what we're going to do is we're going to solve some stuff in the middle. So what I have here is, notice that 2 is less than whatever is in the middle, okay? So 2 is smaller than a number, and then it has to stay smaller than 9. So 2 is the smallest number it can be, but it also has to be below 9. So it would be like me asking you, like we play the game, like, when someone says, can't decide on who's going to get a prize, right? Pick a number between 1 and 10 that's behind my back. Right? Well, no one ever picks the number 50. Well, why not? Because 1 and 10 isn't between, because 50 isn't between 1 and 10, right? So this is like playing the game. Give me a number between 2 and 9 to start. But then I say to you, hey, but you're allowed to add 4 to the number first. So what you actually want to pick are what sets of numbers can you pick, okay, that will end up in between the numbers 2 and 9. So I want to know for this problem, what numbers can I place in for x that when I add 4 to them will then place me between the number 2 and the number 9. Well, the way you do that, okay, is literally what you're going to do here is you're going to solve for the value of x the same way you would for any equation, but you're just going to realize that you're going to simultaneously shift, okay? So if you think you had a bar here on a number line, okay, that was at 2 and 9, essentially what this is saying, because you have plus 4, is basically saying to you, hey, I want you to shift your bar 4 units. Now, I personally know, because I'm your math teacher, right? I know that this bar really is going to get shifted to the left, and you'll see why in a second, why it gets shifted to the left. But I'm going to take this bar on a number line, I'm going to shift it left, and I end up here, and I end up here. Well, if I shift that bar 4 units to the left like that, well, 9 goes to 5, and 2 goes to -2. And what you'll see then is that this is where I have, okay, and if I guess it should be proper here, it should be closed circle, right, because of 2. And I end up with the set of numbers I can choose from that if I add 4 to them, it gives me a number between 2 or 9, okay? So I hope that makes sense there. So now in a second here, let me show you why you shift it to the left, right? So we're going to talk about adjusting both of our endpoints, right? We have to adjust both of our endpoints at the same exact time because of this conjunction and compound inequality. So why does it shift to the left then, Mr. Minger? Well, if you were to think about this and you were to say, hey, how would I solve for x plus 4 to isolate just the x, to identify just the x, right? Well, then plus 4, to make it an identity property, needs to turn into plus 0. Well, how do you turn positive 4 into 0? You write minus 4. And hey, what does the negative 4 mean? Well, negative 4 means go left, okay, of 0. All right, it's the opposite of going to right on the number line. So that's why this thing gets shifted to the left. Now, the problem is that because we're in a conjunction compound inequality, it's not like you can just minus 4 and just choose to change the left input or the left boundary point and leave the right side alone. So if you notice in my little drawing that I had here, okay, you have 2 boundary points, and you got to be thinking about shifting this entire bar. So you can't just say, oh, I'm going to subtract 4 from 2. That doesn't work that way. You've also got to shift the left side of the bar, right? So we don't want to stretch the bar out. We literally just want to shift the bar over. So this is going to also get minus 4. And in the visual demonstration off to the right, you can see that when you do that, or when we visually shifted it to the left, you would notice that you went to negative 2 and 5. Well, the algebraic way now shows it. Well, what's 2 minus 4? So the left-hand side ends up at negative 2, which is less than or equal to the value of x. And the right-hand side shifted over to 5. So what we end up with is the compound inequality of negative 2 is less than or equal to x, which is less than 5. And now when I go to graph this on a graph, literally I'm just going to say, hey, my first endpoint is at negative 2. It's a closed circle. And I have a bar, which means it's connected all the way up to the value of 5. And I put an open circle at the value of 5. Now, if I'm using interval notation here, right, like again, this is just an extra piece here. So to me, honestly, because it's an extra piece, yes, while it may be on your chapter test because I am teaching it to you, I do have to, hold you to some accountability for it. It's not a major piece, okay? So I'm not really going to make it a huge issue if you don't have the interval notation completely down, right? So doing that, my answer for interval notation is, well, what is the smallest number in this entire set? The smallest number is at negative 2, and I will use a bracket. And the largest number I could potentially use in this set would be a 5, but not quite exactly 5, so it's not inclusive. So we'll use a parenthesis. So I just want to choose to do another problem for you as an example here. And in this example, I just want to have a little bit more complexity in the solving of the actual compound inequality. So I'm going to choose to do number 10 down here, just to give you a thing, just to show you, everything you could possibly have, right? So in number 10, okay, when we solve these, we're going to look to the middle, right? So again, think about this thing here, okay? And we have this, right? So we have, boundary points that start at negative 2. So we have this bar, right? That's at negative 2, and it goes over to 4, correct? Now, when you look at the middle, right? Okay, so I want numbers on my bar here that are in between negative 2 and 4. But when you look in the middle here, let's take a look at our operations, right? And if you take a look at your operations here, what you have is you're going to multiply it by 2. And what I want to show you here is if you multiply it by 2, and then after that you do a minus 6, I want to show you kind of what could happen here. And the idea of this is I want my answer for the value of x, that when I plug it in, that it gets me a number in between negative 2 or 4. Well, if you double something, right, well, that meant, okay, that you made something larger, right? Like, think of it, if I go to the ice cream store, I say I want a single dip or I want a double dip. Well, what's the difference between a single dip and a double dip? Yes, the number 1 for one dip or 1 scoop of ice cream, and 2, but the idea is that 2, all right, is 2 times as much as 1, right? So the idea here is if you see this bar, inevitably what's going to happen is that because of this, my number set size is going to shrink. So this bar is going to be cut in half in its length, okay? And then what I'm going to do is I'm going to shift it to the right 6 units. So visually what you're going to find here is that the numbers, right, the distance from -2 to 4 is a distance of 6. And what you're going to find in my answer, right, is that I'm going to actually end up with a bar, right, that's no longer a distance of 6. I'm going to end up with a bar that has a distance of 3. Now, again, why is that, right? Well, because you're going to double these numbers, and then you're going to shift them to the right 6, okay? And that's going to end up being all the sets of numbers that will, when you plug in, okay, to an equation, are going to give you answers that end up being between -2 and 4. So that's kind of what we're trying to solve for here. And here's the visual of that. And again, now I'm your math teacher. I don't expect you, okay, to be coming up with these visuals. What I'm hoping that you get literally is just the process of solving it. And I'm just trying to give you the visuals so that you understand why your answer is going to look the way it does. So, all right, so let's go through this. And let's go ahead and solve this. This last one here is the most difficult. Now, you all should know the first step here to solving x, right? You should notice the thing in the middle there is the most famous thing. And you should be saying to yourself right now, like if I were in class right now, I'd be like, hey, what's my first step? And if you're not saying it out loud or whatever it may be, you should be saying, Mr. Minger, it's distributive property, right? So we're going to go ahead and I'm just going to do the distributive property. Now, do I have to do the distributive property first? No, okay? There's obviously other ways out there for anybody who's watching this and wants to be a critic, okay? But the point is that most commonly, most kids are going to go distributive property. So distributive property it is. So doing the distributive property, I get -2 is less than 2x minus 12, which is less than or equal to 4. All right, from here, I'm going to add 12 to all of this. So I want to solve for x, right? I want to identify the x value. And the idea of identifying x is making it so that you're adding 0. Well, currently I'm subtracting 12 to my x, right? And yes, I know that's a 2x, but I'm currently subtracting 12, and I want it to be 0. Well, how do I turn -12 into 0? Place it with a +12. And then again, okay, you have to understand that when you're doing this, you're not allowed, okay, again, you're not allowed to just go ahead and say that you want to shift one endpoint. You do have to shift all endpoints. So you do have to be working with both boundary points at the same time. So I'm going to go ahead and add 12 here. And then I'm going to add 12 here. So -2 plus 12 gets me +10, which is less than or equal to 2x. And then 4 plus 12, okay, less than or equal to here. 4 plus 12 is 16. Okay, so then now from here, what I'm going to go ahead and do, I'm going to divide everything by 2, divide everything by 2, divide the right side by 2, because again, when I start solving for the middle, it's not like I can choose to just adjust the left-hand point. I also have to adjust the right-hand point. And when I talk about left and right-hand point, again, I am talking about these boundary points, right? So I turned a -2 into a 10, and I turned a 4 into a 16. So this is my new right-hand, or my left-hand boundary point, my right-hand boundary point. So you can't just adjust one of these boundary points at a time. You have to be adjusting both of them. And when you do that, you get 5 is less than x, which is less than or equal to the value of 8. And here's what I want to talk about again. Notice, right? What did I talk about in the beginning with my visual? Right? And obviously I have a more understanding of numbers than you guys do, right? But notice how I did talk about how the distance from -2 to 4 would be a distance of 6. And that now take a look at my end points. It went from 5 to 8, which is a distance of 3. And now that all gets impacted by the type of operation that's in the middle. But what I really want you to get out of this is that you have to understand that there are 2 endpoints. okay? Your one point is at -2 and your other endpoint was at 4. And when solving these, you can't just choose to adjust one side, okay, and not just the other. Or you also can't just decide to get rid of one of the endpoints, right? Like if you take off one of the endpoints, essentially in an inequality, if you chop off an endpoint, you then open it up to infinity. And we're not looking to do that here. We're still trying to keep intact a left point and a right point, like I showed you over here in this bar. We're trying to adjust this bar. We're not trying to chop off one of these sides, right? We're just trying to adjust this bar so that we know what set of numbers we can choose so that I do end up back in between -2 and 4. So that's kind of what we're doing here. And that's where it's at. So let's go ahead and graph this. So again, 5 is less than x. So I'm going to go to 5. So I open the circle at 5. And that's going to be less than these numbers that are in the middle. So 5 has to be less than this number. And then that number, same number, has to be less than or equal to 8. So I'm going to shade that in. You'll notice that I have the values that are in between. So my bar, okay, of numbers, or my strand of numbers, goes from 5 to 8. And that's the end of this lesson, which is already long enough. I apologize for this being a long one, but this is one for the notes that you want to have and copy in. So at this point, you can do your classwork and your homework to do the rest of it.